Okay, so this lesson is all going to be looking at elastic potential energy. Now, there's two equations which we're going to start off with. The first one is F equals KE. And so here, the force is in newtons, the force of the spring, for example. The K is the spring constant in newtons per meter, and then the E is the extension. So the spring constant is going to be a measure of how firm or elastic the object is, and it's very specific to each individual object. Now, if we look at these two materials, this one, let's say, has a lower spring constant, and this one has a higher spring constant. So the one that has a lower spring constant is going to be more elastic, and the one that's got a higher spring constant, that will be more stiff. Okay? Now, if we look at this example now, so the elastic potential energy, that's equal to a half KE squared. Again, K is the spring constant. Here, that's the elastic potential energy, which is the energy transferred to an object as its stretch, and then the extension in meters as well. So, now, if you use 100 joules of energy to stretch a spring, then the 100 joules would be transferred to the spring's elastic potential energy. And then when you let it go and it springs back, it will transfer that 100 joules back out to a different form, like a different form, for example, let's say kinetic energy. Okay, now we're going to look at a couple of examples. You've already got a solution here, but we're going to look at it. So let's look at this first one. So the spring has a natural length of 0.6 meters, but when we apply a force of 14 newtons, it stretches to 0.8 meters. So what is the spring constant here? So what you could do now is you could pause the video and then see if you can have a go at it yourself. So here, for example, first we're going to calculate the extension. So this is a visual example of what's going on. Now, this spring is 0.8, this is 0.6. So the extension is going to be the difference between them. So that's going to be 0.2. And then we're going to just do 14 divided by 0.2 because we're going to rearrange this to find the spring constant. So we're going to rearrange this here to find the spring constant and just do 14 divided by 0.2, which is going to be 70 newtons per meter. Now the next question is this. So what would the elastic potential energy of the spring now be? So if you have a mass attached to the bottom of a hanging spring with the spring constant of 250 newtons per meter and it's stretched from 10 centimeters to 14 centimeters, and you're asked to calculate the elastic energy stored by the stretched spring, then what we're first going to do is, okay, so we've got the spring constant, that's in newtons per meter, that's fine. The extension we can calculate by minusing them, but we also have to put the centimeters into meters. So we want to take them away, so that's going to be 1.4, and then we want to put that into centimeters. So that's going to be 0.014, and so the elastic potential energy is going to be 0.5 or half times by 250 times by 0.014 squared, which is going to be 0.0245 joules. Okay. Now, last but certainly not least, let's look at a specific graph. So this is a force extension graph. So if you have a graph of force against extension like this, then as long as we look at the straight part of the line, the gradient is going to be referring to the spring constant, and the area under the curve is going to be the energy transferred to the spring. So, i.e., the elastic potential energy. So, there is a point here. Oh, sorry. There's a point here, which is the elastic potential, sorry, the elastic limit or the limit of proportionality. So that's where it stops obeying Hooke's law. And all Hooke's law is that force and extension are directly proportional. So just like this. Now, once we've kind of done the whole energy topic, we're going to work by it slowly, slowly. But once we've done the whole thing, I'm going to also upload a load of resources and a load of questions for you guys to try as well. Okay, so that's the end of looking a little bit into Hooke's law and the elastic potential energy. Thank you.